Okay, yeah, let's get started. Okay, so on Monday, we start talking about sound frequency generation, which is that you input two light, okay, they're at different frequency, omega 1, omega 2, and the output is the sum frequency. The output light frequency is the sum of these two, okay, and we said that the reason that we want to look into this is because this is the next simplest nonlinear process following second harmonic generation. And also, as you can see, that this is another way, okay, other than harmonic generation, to upconvert the frequency of the light, okay, from a lower frequency to an upper frequency. And also, this time, compared with harmonic generation, which is exactly doubling the frequency, you have a little bit of control. For example, you can choose different omega 2, and then to get to a different omega 3. Right, so it's more like an upconversion of the frequency. And this is, this sum frequency is practically it's not used a lot in optical domain, but more common in electrical domain. So in electric communication, radio frequency, for example, you can have a signal that's, for example, when you hear about radio, right, the frequency of our voice is only like hundreds of hertz, okay? But that get upconverted using a form of some frequency electronically to a megahertz domain and then send out, okay, through radio. And that's why we can actually hear, well, that's the analog radio, and that's why we can hear, all those voices. And also right now, okay, everything is digitalized. Still, okay, in electronics, people, have signals at, for example, 1 gigahertz band. And then, the way that you can have 5G or in the future 6G is that you can upconvert that into, let's say, 50 gigahertz. Right, and then in 50 gigahertz, it's much larger bandwidth, and then you can put a lot of 1 gigahertz channels there. And that's a use of some frequency, not very useful in optical domain, but very useful in electronics. And from a mathematical point of view, why we talk about some frequency generation is that previously in harmonic generation, what we eventually has is a single equation, and that's first order derivative. In some frequency, okay, by making assumption that, I think here we make the assumption E2 is much larger than E1 and E3, we arrive at this coupled equation where you have E1, the derivative of E1 depends on E3, and then the derivative of E3 depends on E1, right? So this is a very typical coupled equation. And then there's coefficient in the front, which you can define as K1 and K3. So the definition here on the whiteboard is a little different from the definition on the, it's a little different from the definition on my notes. So this one is actually more useful, more common. Okay. And so from a mathematical point of view, okay, the sum frequency is a little bit different. It's a little bit more complicated than harmonic generation, right? In the sense that, you are now a couple mode equation. And a typical way to solve the couple mode equation, for example, is to, if you want to know E1, then you can take derivative of the first equation, and then this side would be second derivative of E1, this side would be first derivative of E3, and then we know the first derivative of E3 is just the second equation, and then you plug this equation back in here. Okay? And eventually, you will get this second order derivative equation of E1. Okay? And it's proportional to this coefficient, second derivative, and then plus a constant, E1 equals 0. And you can do the same to E3. Okay? So from a mathematical point of view, the sum frequency generation, when you're assuming, okay, one of the wave is much larger than the others, will lead you to a second derivative equation. Okay, and when you do that in harmonic generation, it will give you a first order derivative differential equation. Okay, so mathematically there will be some difference. Okay, now let's look at how to solve them, right? So the solution is actually fairly straightforward, and it depends on the sign of K1, K2, right? And here we already know K1, K3. We already know K1, K3 are these two coefficients, so you write them down. And what you can see is that there are a lot of coefficients that are square, so they're all positive. K1, K3, they're wave vectors, they're also positive. And then E2 times E2 conjugate give you the magnitude of E2 square, so this is also positive. So the entire coefficient is larger than 0, okay? So it's positive. So now what you have is second derivative plus a positive coefficient times E1 itself equal to 0. And then the solution to this is very common, is sine and cosine, right? The oscillation term. And here just to emphasize the fact that K1, K2 is larger than K1, K3 is larger than 0. What we can do is we can replace these two coefficient K1, K3. We define it as gamma square we define it as gamma square. So when people see the square, they know that, okay, this is a positive number. So solution of this would be, for E1, okay, would be, well, the two eigen solution. Eigen solution is cosine gamma z, right? So if you plug in cosine here, the first derivative of cosine gamma z become gamma minus sine gamma z, and then you take another derivative, another gamma come out, so it's gamma square, and cosine, and the sine becomes cosine, right? So it becomes minus gamma z. Just write it down; it's easier. Okay, it is equal to minus gamma square cosine gamma z, right? So if you plug this back in here, you will see that, okay, they actually cancel each other perfectly. So the solution is a cosine, and same apply to sine. Sine gamma z is also a solution, eigensolution. And from differential equation that we know that, okay, because the right hand side is 0, so any linear combination of these two eigensolutions is still a solution to this equation. Okay, if you don't believe that, you can plug it in. So we can assume that a general form of this solution, E1z is A1 cosine gamma z plus B1, okay, sine gamma z. And if you look at E3, it's the same, right? E3, because the equation is exactly the same form, so E3 will equal to A2. Let's see, I think I write it down as A3, okay. A3 cosine gamma z plus B3 sine gamma z. Right, so these are the general solution for E1 and E3, okay, with 4 unknown coefficients. Okay, gamma is known, gamma is right down here. And you might wonder, okay, we only define gamma square as K1, K3. So gamma actually has an ambiguity, right? It can be plus the square root of this or minus the square root of this. The fact is that it doesn't matter, because if you look at here, cosine, no matter it's plus or minus, cosine always gives you the same number. When you have sine, gamma, okay, if it's minus gamma, then the way that you can do, okay, to make this term unchanged is to add a minus sign, before the coefficient b1, right? So whether gamma is plus or minus really doesn't matter. You can choose one and then go with it. And normally people go with the plus one. Okay, and to solve a differential equation, okay, and once you arrive at the general solution form, the protocol or the standard procedure is to use either boundary condition or initial condition. Here it's it's the same thing because, well, it's actually the initial condition is that, well, depending on how you call it, but it's actually the same thing because you only have one variable. So one thing you would need to use, okay, is that we know, okay, what's being input on the left-hand side, right, E1, E2, and what we don't know is what at the output side at z equal L, right? So what we know is that at input side, because E1 is the light that you input, so you will assume E1, 0 is a known number. Okay, it's a number that you know because you shine a laser there. And then also, the second thing is that you know that E3, the sound frequency at the input side, okay, sound frequency at the input side must be 0, right? Because you only input E1 and E2. You didn't input any of E3. So at the input port, okay, E3 at z equals 0 has to be 0, right? So what this gives you is that if you use this boundary condition, you can see that E1 at z equals 0, this term is 0 because sine 0 is 0. This term is 1, okay, so this equal to A1, okay? And same apply to E3. At z equals 0, sine term is 0, and the only so E3 equals to A3, right? Okay, equal to A3. And so A3, okay, this term is 0. Okay. Now we still have two variables that we don't know, right? So here you determine A1 and A3. You still don't know sine, okay, this sine. The reason you still don't know B1, B3. The reason you don't know it is because you're checking the boundary condition here. And the sine at the z equals 0 is always 0, so there's no way you can know B. Okay. And from differential equation, we know that, okay, if it's second order differential equation, that you need a second order, well, you need the first order, you need a boundary condition, the value, okay, of E1, E2, E1, E2, E3 here. Also, you need the first order derivative. Okay, that's how you solve the second order differential equation. Okay, so let's look at this term, E1, partial Ez at z equals 0. Okay, at z equals 0. What is that? Okay, apparently we don't know. We don't know. But one thing we do know is that, okay, there's an equation for this, right? The differential of E1 over E1 over z is I K1 E3 at z equals 0. And we know that E3 at z equals 0 is 0, right? Because there's no input of the sound frequency. So this is 0. Okay. And what is partial E1 over partial z? Okay, from your general solution. From your general solution, you have gamma minus gamma A1 sine gamma z plus B1 gamma cosine gamma z. And this whole thing at z equals 0. Okay, again, cosine term equal 1, sine term equals 0. You arrive at B1 gamma. Okay, so B1 gamma equals 0. meaning B1 is 0. Okay, so you get B1 equals 0. So this way you get, okay, your solution for E1. The solution for E1 is that A1 is E1 0. Okay, is whatever your input is. Okay, that's your A1. So E1 0 cosine gamma z. Okay, so this is your solution for E1. Okay, and well, there are many different ways to get E3. Okay, one way is that if you know E1 everywhere, by using energy conservation, you should know E3 everywhere. Okay, but also there are other ways to get this done. The other way is to keep looking at the boundary condition. Okay, here we look at E1 over E3 and then we get B1. So by the same idea, if we do E3 over Z at Z equals 0, if we do this boundary condition, then we should get B3. Okay, we should get B3. So let's look at it. So E3 over Z equal to I, according to this equation, I K3 E1 0. Right, so it's good. It's a known number. Okay, it's a known number. And also according to your general solution, okay, this also equal to minus gamma A3 sine gamma Z plus gamma B3 cosine gamma Z. And evaluate this as Z equals 0. Okay, will give you gamma B3. Okay, so okay, when you take gamma B3 equals this, then you eventually get your B3 is I K3 E1 0 divided by gamma. Okay, divided by gamma. And we also know that gamma is just square root of K1, K3. All right, square root of K1, K3, so that eventually you get I K3 K1 KE1. Okay, that's what you get. So a solution here is that A3 is 0, so you don't have this cosine term. B3 is this term, okay, and times sine, right? So solution is I square root of K3 divided by K1, and then E1's 0 sine gamma Z. Okay, sine gamma Z. So these are this is the complete solution for some frequency generation. Any questions here? Okay, good. So if you look at this, then this is kind of an interesting solution because it's a periodic solution, right? So we again reach at the point where previously, okay, we say that the harmonic generation, the solution is periodic. The reason is that you have phase mismatch, right? So that whenever you go over 180 degrees, then whatever you accumulated is being canceled by the next 180 degree cycle. But here we already assume phase matching condition is perfectly matched, right? That's why we don't have the phase term here. But still, your solution is periodic. And if we draw the periodicity here, you see that they're actually off by 90 degrees, so they're off phase, right? So if this is Z, And let's say this is E square. Okay, if you look at E3, what you have, look at E3 here. Okay, if you look at E3 here, you have E3 square. Okay, look at E3 here, then you will have a sine square function, right? It's going up and down, up and down, up and down. And if you look at E1 here, it's actually doing the same. But notice here, one thing is that the magnitude, the amplitude of E1 and E3 are not the same now, right? So the maximum of E1 is at its input port. Okay, the maximum of E3 is E1, and then there's a coefficient here. Later we'll see, okay, this coefficient means that E3 in some scenario can be larger than E1, in some scenario can be lower. Okay, in this case we just plot the case where it's lower. Okay, so this is E1, 0, your input port. And then what you have is that you drop to 0, come back. I don't have colored here, so let me use dashed line here. Okay. Okay, so let's say dashed line is dashed line is E1. Okay, dashed line is E1. So it's oscillating. Okay, it's oscillating, and then let's quickly take a look after. Okay, let's quickly take a look at the mathematical here. Is that at what situation is E3 square larger than E1 square, and then at what situation E1 square is smaller than is larger than E3 square, right? So it's all about this coefficient K1 divided by K3 divided by K1 square root, right? So if you look at it, K1, K3, they have a common factor here is this part, right? This part is a common factor, and then this part is also the common factor. They have the same magnitude, right? One is just another's conjugate. So this term doesn't change the magnitude. It just change the phase. Okay, phase of the this coefficient. So K3, K1 equal to this term cancel each other. So omega 3 square divided by K3, and then it's K1 omega 1 square. Okay, and then you have E2 I write it down separate E2 because it's a complex number, so I separate E2, okay, as its amplitude and its phase. So the conjugate of E2 would be E2 minus I phi. Okay, so you can also plug in the fact that K1 K is equal to n omega c. Right, n is the refraction index, omega is the frequency, c is the speed of light. So when you plug this in, you will get omega, one omega will cancel out, so you have omega 3 you will have m1 coming from the K1, and then omega 3. The square is cancelled by the omega here down to K3, divided by N3, okay, coming from K3, and then omega 1 here. And then you have a phase, these two cancel each other, you have a phase e to the 2 I phi naught. Okay, So this is K3, K3 divided by K1. And then, so you can keep writing this. Okay, plug this back in, and then you have I e to the I phi knob square root n1 omega 3 and 3 omega 1, okay, E1 knob sine gamma z, okay, sine gamma z. So this is the E3 expression when you plug in what K3 and K1 is. Okay, so few comment here. First is that for some frequency generation, when it's phase matched, right? So the refraction index actually changes very little. Usually, the best way to achieve phase matching is that the refraction index is not wavelength dependent at all, right? So that means the momentum, okay, is purely a function of frequency, and then you can satisfy momentum conservation everywhere. Okay, and so usually, okay, when seeing this, you can assume n1 is very close to n3, so that this coefficient really doesn't matter that much. The factor that really contribute to the magnitude of E3 here is the omega 3 divided by omega 1, right? So omega 3 divided by omega 1, right? And as you can see here, because it's some frequency generation, right? So omega 3 is omega 1 plus omega 2. So omega 3 is always larger than omega 1, right? It's always this case. So, and also in a lot of times omega 3 is actually much larger, okay? Because usually you would say omega 1 and omega 3 to be relatively close to each other. So this term here, E3, okay, its magnitude is usually larger than the amplitude of E1, okay? And okay, let's just get that out of the way, and then we can start some physics analysis. Now the question I have here is that does this oscillation behavior make sense? Can we actually tell from the very beginning the some frequency generation, the amplitude would oscillate, or do we really have to go through all the trouble of solving the math here, right? The answer is actually, we know this, we can predict this from the very beginning, okay? If you look at the physics process here, what really happening for some frequency generation is that you have a photon of omega 1, and then you have another photon of omega 2, right? And then you generate an omega 3. Okay, so when this process happened, you lose a photon of omega 1, you lose another photon of omega 2, right? So what does that really mean is that your E2, okay, here we have assumed that E2 is much larger, so let's not worry about E2 here. So let's say E2 is a lot of omega 2 photons, so it doesn't matter. But E1, okay, they would decrease when you generate a some frequency photon, right? Because you have one less photon in your omega 1 light, right? So the more omega 3 you generate, the less omega 1 you have. And now imagine the extreme situation when you now have no omega 1 photon. Then this some frequency process has to stop, right? Because you have no supply of omega 1 photon. Right? And also, from where we learned in second harmonic generation is that whenever your field, okay, your omega E1 and E2, when they start to decrease, your efficiency of this nonlinear process also decrease, right? Because we learned that, okay, the efficiency of the nonlinear process change nonlinearly, okay, with your input power. So now if your input, if your field of your input, okay, is dropping, then the output, the increase of the output should also drop. Okay, this can be clearly seen here as this equation, right? You have the rate of change for E3 is proportional to E2 multiplied with E1, right? So if your E1 decrease, then of course your E3, the increase rate of E3 will slow down, right? So that's why when you look at here, when you that's why when you look at here, when E1 drop all the way to zero, okay, the rate of change to, let me see if this is correct. Right, the E3 is no longer changing, it's no longer increasing at all, right? So the slope of E3 change over Z, okay, goes to its maximum. And another way to look at this is that another way that you can keep analyzing this, okay, what will happen after that, right? We'll kind of show you guys what will happen in the first phase is that when you keep increasing E3, okay, your E1 will drop. That will slow down the increase of E3, and eventually it will stop somewhere here, right? Right. So this part is fine. This part is very easy to see from simple analysis. But why does it oscillate? Why does it oscillate? So if we look at this point, okay, you have a strong E3 and you have 0 E1. And if I look at this as the input to the rest of the waveguide, then what process can I expect? What you can expect is that this is again a sum frequency, right? You have E2 there, and then you have E3, okay, instead of E1. You have a non-zero E3, and then you have a 0 E1. So from this point, okay, let's call it point A. Point A. If you look at point A and looking to the right of the waveguide, what you're looking at is that, okay, there's E2, there is E3, and you have E1, at this point equals 0, right? So you kind of reverse the row. You reverse the row of E2 and E1, well, E3 and E1. Okay, so in this way, what you can expect is that, okay, this two wave will now start to generate E1. Right, this two wave will start to generate E1. Okay, and when it starts to generate E1, okay, then E1 start to increase. Then of course, when you generate E1, you consume photon from E3. Then E3 will start to drop, right? And this behavior, okay, happened periodically, okay, as you move along the Z direction. Okay. Any questions? Okay, good. So as a summary, okay, here, what we can see, okay, is that whenever you generate an E3 photon, you consume an E1 photon. And then when all E1 photon is consumed, then the process starts to reverse, and then you start to convert E3 photon back to E1 photon. So in this process, you can kind of very easily you can see that there's a photon number conservation between omega 1 and omega 3. Omega 1 and omega 3, right? Whenever you need to generate omega 3, you have to consume omega 1 and vice versa. Okay. Now the question I have here, it looks like if you consume the number of photons, then why does the amplitude of the electrical field maximum point of E3 is not equal to the maximum point of E1? Right? We say that there's a conservation law here, but why E3 is always larger than E1? Does that mean there's extra photon coming in, or does that there's extra energy coming in? The fact is that, it's neither cases. These two doesn't violate each other. The real reason that E3 can be larger than E1 is exactly because the photon number is conserved, and the fact that omega 3 is larger than omega 1, right? So each omega 3 photon carries more energy than the omega 1 photon. And where does that energy come from? The energy is coming from E2, right? Because omega 1 plus omega 2 give you omega 3, right? So you take energy from E1, but also from E3 but also from E2, to generate E3. So if you take a look at the note, page 23, there's a calculation, showing you that this coefficient here, N1 omega 3 and 3 omega 1 square root of this coefficient here, precisely ensure photon number conservation. Each omega 1 you consume, you generate omega 3. And then since it's kind of boring calculations, I'm not going to repeat here. The way that you calculate the number of photons you generate is by, the key, in this calculation is that the power is equal to this. We've looked at this many times. And the photon, power means energy per unit time, right, flowing across a cross-section. And then if you want to count the number of photons, per unit time going through a cross-section, you just divide the power by the energy per photon, right? So this is energy per unit time. And then if you divide it by the energy per photon, then you get photon per unit time. So this gives you a photon per unit time going through a cross section. And then here you already start to see, there's n divided by omega. This is n1 divided by omega 1 and 3 divided by omega 3. So if you plug this back in here, you will see. If you plug this back in here, you will see that these terms, they cancel each other perfectly, and then you have a photon number conservation. And finally, one more comment is that this phase term here. So my question is, does this phase term matter at all? Should we keep it? Anyone want to make a guess? So here, the phase term, actually you can make an argument, well, it's not really an argument, it's a fact, that this phase term has no physics effect at all. The reason is in optical, the optical phase, in optical system, the absolute phase actually doesn't have any physical meaning. You can't really measure it. The reason is this. Okay, when you define a wave, right? We define a wave. You have the frequency oscillation term. You have the wave. Well, you have the spatial oscillation term, and then you have a phase, initial phase. Okay. You can easily see that this phase is actually depend on how you set up your coordinate, right? If you change your t from t to t minus t naught, right? If you change the 0 point of your time, right? Then this can easily go to e naught, e to the minus I omega t plus I omega t naught plus I kz plus I phi, right? So you get a new phase. Now your phase is omega times is phi plus omega t naught, right? You can do the same by moving the 0 point in your space, right? Where you start to say, okay, z equals 0. And because we know that you can't say, okay, there's an absolute time 0 point for all the universe, or absolute position 0 point, okay, in all the space. You can say that the space and time, they're all relative, so that for different system, okay, by defining the starting point and starting position, you can kind of arbitrarily change this phase, And therefore, okay, in our system, you can change the time 0 point to always make this phase 0, okay, or make this phase any arbitrary number. And what that means is that in your measurement, in your physics experiment, you should not see any, you should not observe any physics phenomenon that would depend on this phi 0. Okay, it means that you simply cannot measure any phenomenon that would depend on this. Okay, so therefore, in almost all calculations, when this happens, we will erase, okay, this term. We'll simply say, okay, by rotating the frame or by resetting the frame, we can always set phi to 0. Okay. But now my question is that, okay, can you do the same thing now for E1, right? Because when we do this calculation, we assume that E1, E2, they can all be complex number, right? You can always carry a phase. So if we do this to E1, if we do this to E2, can we also say, okay, we set the frame for E1 and we make E1 a real number, right? It's very tempting to have everything in real number. Okay? And the answer to this is actually no. The answer to this is no. And you might wonder, okay, what's the difference here? Why you can do this to one but not to the other? The reason is that if you choose to select different time 0 point, you can only do it once, right? For your measurement, you have to select one time 0 point, okay, and then apply it to this time 0 point to all your measurement, all your calculation, right? So in here, you will have E1, e to the minus I omega t plus I kz plus I phi 1. Okay, this is your E1, and then your E2 okay, 2 I phi 2, right? So here you can change the 0 point in your time frame, okay, to here to make phi 2 equal to 0. Okay, you can do that. But remember, E1 and E2, they're in the same frame. So when you do this to make this term disappear, okay, you already select your frame of time, okay, and you cannot do that again to set phi 1 to 0, right? You cannot do that again to phi 1 to 0. Of course, you can say, okay, can I set z, okay, so that is 0. You can try to do that, but it doesn't work, right? Because again, if you set z to cancel this, then you also change the z here, and then you add the phase term, okay, to here, right? So, so what this tells us is that in an optical system, the absolute phase, the global phase, okay, the global phase doesn't matter because you can always change time 0 to add a constant phase to every frequency component. Okay, that's a global phase. The absolute phase. Okay, so the absolute value of phi 1, phi 2, okay, doesn't really matter. What really matters is that when you change this, what really matters is the relative phase between phi 1 and phi 2. Okay, so when you, for example, when you change time 0 here and cancel out and create a term that's minus I phi 2, okay, that somehow cancel out this, you will also create a minus I phi 2 term also in this term because they share the same time frame. Okay, then eventually what you will get is I delta phi. Okay, the phi difference between the two waves. Okay, so that's why in optical system and also in electrical system, the absolute phase, okay, doesn't matter, but then the relative phase, okay, will actually, the relative phase will actually change. Well, actually, is something that observable and cannot be arbitrarily set. Okay. Other questions? Any questions? So now let's do a quick summary here and then see what's lacking. Okay, what's missing in some frequency generation and also in harmonic generation. In harmonic generation, what's missing is the flexibility of determining the output frequency, right? No matter you only have one input frequency, and then the output is always the twice the frequency, okay, of the input. And in some frequency generation, okay, it has the flexibility to tune, the output frequency, by changing. Okay, if your input is always omega 1, then you can change omega 2, okay, to tune it. But what it suffers is that it looks like your output, the number of photons in your output is capped by the number of photons in your E1. All right, so there's no amplification process here. What it is at its best, you could do a 1-to-1 conversion, right? 100% conversion from E1 to E3, and that's all you can do. And that's a little bit, disappointing because if you guys know electronics, you know that amplification is really, really important, right? That's how you get transistors, and that's how you use small signals to control large signals. Okay, so is there a physics process, optical nonlinear process, that can not only change a wavelength, change a frequency, but also it doesn't have this oscillation, but keep growing, assuming the phase is matched, right? Assuming the phase phase matching condition is satisfied, right? If you don't have phase matching condition, then of course you always has this oscillation. Okay, and the way to do this, is to do difference frequency generation. Okay, so this is actually the reason why difference frequency generation has, is actually one physics process that's being widely used in in many labs, including in UVA. In physics department, there are a few groups that use this frequency difference generation process for their quantum experiment. And on the other hand, some frequency generation people actually don't really look at it that much. Okay, so what is difference frequency generation? Okay, it's of course a reverse process, right? Reverse process of some frequency. What you would say is that, okay, if your input let's say here, if you input omega 1 and omega 3, okay, and the output omega 2 equals to omega 3 minus omega 1, right? Omega 3 minus omega 1. Okay, some frequency, difference frequency generation. And the physics process on the photon level of course you have omega 3 larger than omega 1. Okay, on the photon level is that the input, if you write down this equation, right, on the photon level is omega 3 minus omega 2, omega 1 equals to omega 2, right? So it's exactly the difference frequency equation, but you multiply h bar there. H bar omega gives you the photon energy, right? So you have a photon at omega 3 on the left-hand side. And now it's interesting to how we interpret the minus sign in front of omega 1, right? How we interpret that. So previously, for example, for harmonic generation, if we have 2 h bar omega on the, if we have h bar omega plus h bar omega equals to h bar 2 omega. Okay, we said that the photon on the left-hand side, 2 photon, is annihilated or consumed to generate a photon on the right-hand side that is at frequency 2 omega. Right. So here, what we are doing, okay, if you look at this, is that there's no, here every term is positives, right? So there's no clear way to kind of see what this minus sign is. So the way that you can try to interpret what difference frequency generation really is at a photon level is that you move this term to the right. Okay, so that every term here is positive, and then you can use the exact interpretation you build up, okay, from harmonic generation. So then what this says is that, okay, 1 photon at frequency omega 3 is consumed or annihilated, and then it generates a photon omega 2 and a photon omega 3. Sorry, a photon omega 2 and photon omega 1, right? And because omega 1 and omega 3 are two input, okay, then equivalently it looks like, okay, you do a difference frequency generation. So in this process, what you're looking at here is suppose originally you have a lot of omega 3, right? That's your pump. You have a lot of omega 3 photon, and then you have one omega 1 photon. Okay. Then after some frequency generation, what happens is that you lose one photon. You still have a lot, okay? You lose one photon in omega 3, right? Annihilated one photon in omega 3, and then you generate a photon in omega 1, and then you generate a photon in omega 2. Okay, so in this process, you will see E3, the amplitude of E3 of this difference frequency generation decreases, and E1, E2 both increases. And so if we work at the regime where E3, okay, is much larger than E1 and E2, then you can neglect the change in E3. Okay, then what this process typically do is that when you generate a difference frequency photon at omega 2, you also generate a photon at omega 1, and E1 and E2, they increase at the same time. And because we know that you can kind of already guess the difference frequency generation, the differential, okay, here, it must be proportional to the field of E1 and then the field of E3, right? And because we're using this assumption that E3 is much larger than other field, then you can see that when E1 change, when E1 increase, then the rate of change in E2 will also increase, right? Will also increase. So in this difference frequency generation, under this regime, okay, it's possible, that your E2 can grow exponentially, right? Because when you grow, E1 grow. When E1 grow, your rate of growth also increase, right? So this is a positive feedback process, which is very different from the sum frequency generation. Okay, so if you plot, this is Z. This is the I don't have that on the chart. Anyway, this Z, this is number of photon in your mode. Then what you have, originally you have, let's say this is number of photon in N1 mode, omega 1, okay, that's the input. You would increase, okay, and the number of photon in N2, okay, it will also increase. And then they are increasing at the same rate. So the distance here, okay, the distance here is always the same because whenever you generate omega 1, you also generate omega 2, okay? And the rate of change should increase, okay, because when you have more photons in your, field, okay, you're more likely to create the nonlinear phenomenon, okay? So you can imagine the process go like this. And of course, this process has a limit. Is that here we have already, well, the reason that we get this get this result, we get this analysis work, is because we have assumed that E3, the field in E3 is much larger than E1 and E2. Okay, so whenever your number of photons is approaching the number of photons in omega 3, then it will start to saturate, and then there's other effect. Okay, but normally, okay, when people do experiment, we work in this regime. Okay, and And as you can see here, the as you can see here, the this process, okay, this process, although it's difference frequency generation, okay, you generate N2, a photon, but what does it do to E1? What does it do to E1? Omega 1 photon. Okay, what it really does to E1 is that it also increases the number of photons in E1, right? So this is an amplifier. Okay, this is an amplifier. So input E3 and E1. Okay, what will happen is the small signal, if you have, a little bit, just a little bit of photon in E1, omega 1. Okay, that's being amplified here, and so this is difference frequency generation. One of the critical application here is the amplification. Okay, and then there's a name for this. This is called parametric amplifier. Okay, parametric amplifier. And why is it called parametric? What does parametric mean? And what other amplifiers we have? Okay, so a more typical amplifier in optical world is something like an optical amplifier. Well, something like fiber amplifier, erbium dope amplifiers. So when people say amplifier, what they typically mean here is that, let's say this is a fiber amplifier. So in a fiber amplifier, okay, there's doped ion, okay, erbium, for example, that, while this is a two-energy system, that the electron literally go to the upper state. Okay, and then when the photon come in here, there's the stimulated emission. Okay, when this photon come, that one of the, well, if you have one photon here, then one of the electron is likely to come down. Come down a straight line. Okay. Likely to, you can induce a electron to come down and then generate another photon. Okay. And then this process can keep happening. Okay. Then another one can come down, and then okay, you can have 3 photons. And keep going, keep going. Okay, so this is a typical optical amplifier structure, fiber amplifier. And the key feature of this amplifier is that after the light is being amplified, okay, the state of the amplifier actually changed, right? Before, let's say you have n electron, okay, on top, and then you only have 1 photon, okay, 1 photon. And after amplification, if you now have m photon, m plus 1 photon, then the electron on the excited state, reduced to n. Let's not call it electron, but call it upper state. Okay, the electron at the upper state now reduced to the original upper state electron minus the number of photons generated, generated here, m. Right? This is because every time that a photon is being emitted, an electron has to come down, okay, from the excited state to lower state, and to emit a photon. Right? So if you look at the amplifier itself, look at the electron in the amplifier itself. After amplification, the state changed. Okay, so this is a typical amplifier. So what do we mean by parametric amplifier? Parametric amplifier means that after amplification, the amplifier, the material, okay, the material, if you look at the piece of material, the material actually doesn't change at all, okay? And how is that possible? This is possible is because the energy, okay, supplied to this amplification is not from the material, right? In a conventional amplifier, okay, the energy is stored in the upper level electron, okay? Whenever you come down, you lose energy, emit a photon, right? So that's why if you think about energy conservation, then a conventional amplifier has to change after amplification. But here, for parametric amplifier, for example, difference frequency generation, what happens is that you consume omega-3 photon, okay, annihilate omega-3 photon, and then to generate omega-1 and omega-2, right? So the photon is coming, so the energy is coming from your optical light of omega-3, right? And then there's energy conservation, omega-3 plus equals to omega-1 plus omega-2, right? So after this process is finished, your let's say your material, if it's originally at ground state, okay, absorb omega-3 photon, go to excited state, and then emit 2 photon, and then coming down, right? So of course, this actually doesn't happen. This is a virtual process. So after the parametric amplification, your material stays exactly as its original state, okay? This is because the energy is supplied by the optical light instead of the material itself, right? So the parametric amplifier, the key of this, okay, is that it doesn't change the state of the material.
Excuse me, those difference, those generated like photons, I mean, they again, I mean, involved in a circulation to generate more, to like to cause some of the electrons to the upper state, and then again more and more like what's the name, like photons. That's why we call it like amplification or something like that.
Yes, exactly. That's the definition of optical amplifier, right? Optical amplifier means that the output photon, the number of output photon is more than the number of input photon.
So in this case, for example, HW3, I mean, generate like HW1 and HW2, and then HW1 and HW2 again cause, for example, HW4, HW5, and so on. Is that right? Or
No. It's not like this. Okay, let me. Yeah, that's a good question. Let me plot this in a more clear way. Okay. Okay. So let's go very extreme, right? So let's say originally you have a lot of omega-3 photon. Okay. And then you have one omega-1 photon, and then 0 omega-2 photon, right? This is your initial state, okay? Yes. And then you go into this difference frequency generation, and what happens is that you consume one omega-3 photon, right? And then you generate one omega-1 and then one omega-2 photon, right? So in this sense, omega-1 is being amplified, right?
Yes.
And then this process can keep happening, is that you can consume another omega-3 photon to generate one omega-1 photon and then another omega-2 photon.
Oh, okay.
Right, so there's only three frequency being, yeah, in this.
And this is keep going until we consume all the omega-3 photons. Yeah?
Yes, exactly, yes.
Thank you.
Yeah. Okay, yeah, and so is for the conventional fiber amplifier, is that what's being amplified is the number of photons. The frequency doesn't change. Okay, that's usually the meaning of amplifier in optics. Okay.
Yes.
Yeah. So parametric amplifier, the difference between conventional amplifier and parametric amplifier is that after amplification, the state of the state of the material doesn't change. Okay, and why is that important? Why is that important? That's important for a few reasons. The first is that if you need to change, if your electron needs to go down and go up, go down and go up, what that means is that actually takes time.
Yes.
Right? So parametric amplifier is very, very fast compared with conventional amplifier. Okay? So parametric amplifier is used to amplify, a lot of times amplify femtosecond lasers, that the laser pulses with the pulse width of like a few femtosecond. Okay? So that's one use of parametric amplifier. Okay? And the second use of parametric amplifier is that if you look at it, the conventional amplifier, because it actually involve the electron transition, right? So its energy, okay, the frequency it can amplify, h bar omega, has to be very close to this, the energy difference between these two states, right, in your material, right? So the conventional amplifier, okay, if you want to change the frequency, amplify a different frequency of light, you need to look for a different material. Okay, and then people have looked at it in the past 40 years. Okay, and then Erbium is one for 1550 nanometer, and then sorry, I forgot how to pronounce this. This is for 1060 nanometer light, but there's only a few options there, so you can't really, easily move to a frequency that you want to amplify. But on the other hand, parametric amplifier, you see that the amplification frequency here, omega 1, omega 1, it's arbitrary here, right? We didn't actually have a constraint on what omega 1 can be, right? Because the process, in this process, omega 3 is consumed, generate omega 1, and then generate another omega 2, right? And this is a virtual state. The electron actually do nothing here, okay? So in this way, it means that your parametric amplifier can be moved to any frequency, okay, as long as you satisfy the phase matching condition. Okay, as long as you satisfy the phase matching condition. So the only part that you have to worry about is not to worry about, okay, what material you select, but instead you need to worry about how you can satisfy the phase matching condition. Okay, so that means you need to have right. That means when you satisfy energy conservation, you also need to satisfy momentum conservation. Okay, as long as these two are satisfied, you will have a very good parametric amplifier. Okay. Do you guys have any other questions? Okay.
No.
Okay. Then next Monday we'll start to talk about the math of the difference frequency generation, and then show you guys, really prove you guys, okay, it's really an amplifier, and then and then also point out a few applications of this process. Okay, thank you guys.
Sounds good. Thank you very much.